Our next speaker is Daniel Agterberg, who will tell us about topologically protected nodes, application to strontium-ruthenate and uranium-tellurium-2. And I'll give you a 5-minute warning before your time's up. Okay, so please, Daniel.
Okay, well, thank you, and thank you to the organizers for giving me this chance to speak. I'm really enjoying this conference much more than I thought I would, and so that's a credit to the organization. So what I'm talking about is topologically protected nodes, and this gives me actually a framework in which I can discuss both strontium-ruthenate and uranium-tellurium-2. And what I'll do is I'll give a quick introduction to a topological nodal classification that I prefer, and then I'll jump into a brief description on my discussion in strontium-ruthenate on the possibility of having Boguslavov Fermi surfaces in strontium-ruthenate. And then I'll spend the bulk of the talk talking about superconductivity in uranium-tellurium-2, which I think is a subject that hasn't really been discussed very much in this conference. The work on strontium-ruthenate is really due to calculations from Henry Menke and Han-Gil Su. And the work on uranium-tellurium-2 is really a theoretical perspective on experimental results that come from Ian Hayes, who's in Maryland, and Jean-Pierre Paglione's group, and then D.D. Wei, who's in Stanford, and Aaron Kapitolnik's group. And if I have time, I'll talk about some new theory results on uranium-tellurium-2. Okay, so why these two materials? Well, the main reason I want to talk about them is that they both have experimental evidence that they break time reversal symmetry. And so here I show the original data from Graham Luke and co-workers for strontium-ruthenate, where he's measuring the μSR relaxation rate as a function of temperature. And you can see that as you go below TC, you see an onset of this μSR relaxation rate, which tells you that there's some sort of magnetism forming inside the superconducting state. This experiment was later repeated or verified by Aaron Kapitolnik's group, and then by Zia and Aaron Kapitolnik, and then later, more recently, Grienko and co-workers in Dresden have repeated these μSR experiments in strained samples of strontium-ruthenate. In uranium-tellurium-2, in this work, D.D. Wei and co-workers saw that the polar Kerr angle increases as you go below the superconducting state. And the difference between the red and the blue data is the applied direction of magnetic field. So in the first case, it's say in the positive c-axis, and in the other case, it's in the negative c-axis. And that field orientation will play a role in trying to identify what kind of order parameter symmetry we have in this material. Okay, so these are both unconventional superconductors, and both spontaneously break time reversal. And it's this broken time reversal that is my intertwined order in this conference. So what I'm going to argue today that in both these materials, we have a sort of a unique circumstance in that they're nodal, but the nodes are not given by symmetry, but rather they're only dictated by topology, meaning that the nodes do not sit at points in momentum space that are dictated by symmetry, but rather they can sit in arbitrary points in momentum space, and these nodes are topologically protected. Okay, so let me turn then to the key arguments behind this topological protection. And really the essential point is to realize, and something this was emphasized by Phil Anderson years ago, that superconductivity is stabilized by key symmetries. In particular, to have a weak coupling instability, you have to have fermions that are at momentum k that are degenerate with fermions at momentum minus k, and the only way to guarantee you have that degeneracy is through symmetries. And in 3 dimensions, there's only 2 symmetries that allow that, and that's inversion or time reversal symmetry. Now, in both strontium-ruthenate and uranium-tellurium-2, the normal state has both these symmetries, and that'll mean it has the product of the 2, and when you square this, you get -1. And this is a symmetry that takes k to k, because both inversion and time reversal take k to -k. And that means that we have a Kramer's degeneracy at each momentum k, and this Kramer's degeneracy is often called pseudospin, which we can assign to, say, a spin up and a spin down. Okay, so now let's turn to making Cooper pairs from this pseudospin. So we have two states at momentum k and two states at momentum minus k, and from that we can make 4 types of Cooper pairs. And I think this is familiar to most of you. We have to satisfy Pauli exclusion, and so the wave function, the fermionic wave function has, or the superconducting wave function has to be anti-symmetric under the interchange of the fermions. And with parity symmetry present, we actually have a nice classification for this. This anti-symmetry can be carried in the spin channel, and we get a pseudospin singlet. And then under parity symmetry, we're then required that this is an even parity state, and so it's characterized by a scalar wave function psi of k that satisfies psi of k equals psi of minus k. Conversely, we can have a pairing that is symmetric in the spin channel, and that's what's drawn down here. And in this case, then, anti-symmetry of the Cooper pair wave function requires then that this function d is anti-symmetric under sign change of k. And so that's where the odd parity comes into play. This is an odd notation, perhaps, if you're looking at it in terms of this components of d. But the important point is that this vector d rotates as a vector under spin rotations. And I'll talk a little bit more about these d vectors as we go along, because I realize that we don't often speak that much about spin triplet superconductors. Okay, and so here, so what I've looked at now is the role of time reversal and inversion symmetries in giving rise to spin singlet and spin triplet Cooper pairs, and that's what I've rewritten here. But we know that in practice, we have further symmetries in our system typically, and those further symmetries dictate the structure of Cooper pairs. So in particular, we say the gap functions belong to certain irreducible representations of those symmetries. And so just as an example, and to throw out a few pairing states that I'll talk about throughout this talk, I included some examples of representations for the group D4H, which is the rotations of a square. And so here I start with a spin triplet D vector state, which I'll call the helical state. And here what's important is this D vector I've purposely put in the plane, so it has components x hat and y hat. This is we call this A1U. And here's a very familiar state. This is a D wave state. This is spin singlet, and it has a momentum dependence kx squared minus ky squared. This state has nodes that we're all familiar with, and those nodes, their position is dictated by symmetry arguments. And then we have two-dimensional representations in this group, the EU and EG representations. And that means we have 2 degrees of freedom for describing the Cooper pairs. And we can choose any relative phase between them in practice, but of course group theory restricts those choices. And in practice, we can find a chiral combination, as I've shown here. And this was believed to be the superconducting state of strontium ruthenate until maybe a year and a half ago or so, or 2 years ago. And here, this state breaks time reversal symmetry, and that's governed by this factor of I between these 2 components. And so this carries an angular momentum. Conversely, we can have a nematic state, which is just a real combination, and that's argued to be relevant for copper doped bismuth selenide. And also we have a 2-dimensional D-wave-like state, which is even parity. And this can also be broken time reversal symmetric or not. And here the broken time reversal symmetric has been argued recently to be relevant for strontium ruthenate, though there are other possibilities that might apply there. But in the context of strontium ruthenate, I will focus on this state throughout this talk. All right, the key point I want to emphasize here is the symmetry here is high enough such that we have doubly degenerate representations from which we can make broken time reversal states. Okay, and we'll come back to that point later on. Okay, so just for those of you who are not so familiar with D vectors, I thought I'd put a slide up to tell us a little bit about D vectors, in particular the response to magnetic fields. And so here we all know that, so here I'm looking at spin susceptibility, and I'll also talk about Pauli suppression of magnetic fields. There's always orbital suppression, but I'll talk about Pauli suppression. For spin singlet superconductors, we know that since spin singlet objects carry no spin, at 0 temperature, they should have no response to a field, and so we expect the susceptibility to go down to 0, okay? Now, that's not the case for spin triplet superconductors. For spin triplet superconductors, what matters is the relative orientation of the D vector and the magnetic field. So loosely speaking, we can say that the Cooper pair spins are perpendicular to the D vector. And so if D dot H is 0, then we expect to see no change in the spin susceptibility. And so I've illustrated that here for this D vector oriented along the C axis. And so if I apply the field in the plane, you see no change in spin susceptibility in this simplified picture. However, if the D vector is parallel to the applied field, then you'll see a suppression in the spin susceptibility, and that's what I'm showing here. And just to drive that point home, I'm also illustrating what happens for the helical state. And so here the D vector is in plane. If I apply a field in plane, I get some suppression of spin susceptibility. That's because we're partially orthogonal and partially perpendicular to this field. But if the field's applied along the C axis, then again, D dot H is 0, and we get no change in spin susceptibility in that case. If I have time, I'll talk about the relationship between this and Pauli suppression of the upper critical field. But the thing to remember is if D dot H is 0, then there should be no Pauli suppression of the upper critical field. And this is in the context of uranium tellurium 2. I might talk about this. Okay, so that gives you some feeling for the D vector. Now let me jump into the nodal classification. So here, many people have actually carried out a topological nodal classification for superconductors. And I've written I guess what is a subset of those people here. And I apologize if you're watching and your name isn't here. You can tell me and I'll include you. And the main difference between these classifications is what symmetries you include in your theory. And as I argued before, if we're studying superconductivity, there's really two key symmetries we should include because these are the symmetries that actually make the superconducting state stable. So if we have a superconductor without time reversal and inversion symmetry, then we expect that superconductor no longer has a BCS instability and so isn't necessarily a stable state anymore. So it makes sense to include time reversal and inversion symmetries, and all superconductors have particle hole symmetry. And so any classification should include that. And it turns out amongst these authors, there is a paper by Thomas Bezusek and Manfred Siegrist that included exactly these three symmetries and carried out a classification of nodes based on this. The key point in this is that time reversal, inversion, and charge conjugation all take momentum to minus momentum, k to minus k. But if we want to classify nodes and momentum states topologically, we want to actually have symmetries that take momentum k to k. And so that means we want to look at products of these symmetries, time reversal, inversion, and charge conjugation. And the relevant products then are this time reversal times inversion, charge conjugation times inversion, and this charge conjugation times time reversal symmetry. Now, this symmetry and this symmetry are both anti-unitary, and this symmetry is unitary, and that might begin to remind you of the so-called tenfold way classification we have in topological superconductors and insulators for real space excitations. And indeed, there's an exact mapping between this theory and that theory, just a slight difference in the definition of the symmetries. And so as a result, in general, there will be 10 classes, the Altland-Zirnbauer classes that will result. But in practice, or for a superconductor, only 4 of these classes can actually be realized. And the reason for that is quite simply that we always have this symmetry in some form. This symmetry will either square to plus or minus 1 depending on the inversion symmetry. And if we have time reversal symmetry, that symmetry squares to minus 1. And so that limits the number of classes we can have that appear. And that's these 4 cases. And it turns out it's actually relatively simple to understand these 4 cases. So what I'm showing here now is the results of this classification. And what it tells us is whether we have point nodes or line nodes, which are familiar low energy excitations in superconductors. But of course, in a 3-dimensional Brougham zone, we can also have Fermi surfaces, and that's allowed and could be topologically protected. All right, so these 4 classes are as follows. The first is even parity, and it has time reversal symmetry. In that case, an example of that is our usual D-wave superconductor, kx squared minus ky squared. And this can have topologically protected line nodes protected by twice an integer. Or we can have an even parity broken time reversal superconductor, and an example broken time reversal superconductor. An example of that is a chiral superconductor, like in the context of strontium-ruthenate. And so here I've drawn a KZ, KX plus or minus IKY. And this, interestingly, has topologically protected Fermi surfaces. And I'll talk about that a little bit in a minute. And then we can go to the spin triplet or odd parity states. They can have time reversal or not have time reversal. If they have time reversal, then we find there are no topologically protected nodes from these symmetries, time reversal and inversion. And if they break time reversal symmetry, like this chiral state that was argued to be relevant for strontium-ruthenate, then it turns out that they have topologically protected point nodes, and these point nodes are Weil nodes. All right, and so I'm going to focus on these two cases in the following. I'm going to argue that this is relevant for strontium-ruthenate, and this is relevant for uranium-tellurium-2. Oh yeah, and I should mention, if you may have heard me speak before about topologically protected Bogoliubov Fermi surfaces. I'm not going to actually give a lot of that discussion here, but you can find some details of that work in this paper here. All right, so that was my introduction, and now I want to turn to my example or my real materials. And the first is strontium-ruthenate. All right, so yesterday we saw actually a couple nice talks on strontium-ruthenate, one by Jörg Smalian and one by Andrew Mackenzie. And one of the key takeaways from these was this is a singlet superconductor. So the idea that this could even be an in-plane triplet superconductor looks to be in very shaky ground, and the most likely possibility is that it's singlet. In addition, we briefly heard about some recent experimental measurements, well, maybe not so recent, but that will appear in Nature Physics soon. And that's there's a shear C6 modulus jump at TC. And the only way that can be understood is if the order parameter has two complex degrees of freedom. All right, and so this is done by the Cornell group and by the Sherbrooke group. And so taking this data together with a broken time reversal symmetry, a natural possibility then is that you have this chiral KZ, KX plus I, KY superconductor. And I should point out there are other possible states that have been pointed out. For example, there is a D plus IG state that has been argued to be relevant as well. All right, and so the reason people did not discuss this state very much in the past was because it's not very easy to understand how you can get this in a quasi-two-dimensional material like strontium-ruthenate. And so to the credit of Han-Gil Su and Henry Menke, they found that indeed it's possible to stabilize this state. And I won't go into too many details, but the key point is that we have a Hund's rule local pairing mechanism. And this kind of pairing mechanism favors orbital singlets, spin triplets. And if we include to this spin orbit coupling and C-axis dispersion, we find that this state can be stable for very realistic electronic structure models of strontium-ruthenate. And if you have questions, I can show you more details about that later. But because we have a theory that stabilizes such a state, we can then calculate the low energy excitation spectrum. And sure enough, we find that there are Bogoliubov Fermi surfaces, and they're protected by a Z2 invariant that I haven't really discussed. And so that's the first result I wanted to highlight. And you can see that here you have nodes all over the place, and some of them are clearly not dictated by symmetry. The one thing I do want to point out in this picture is that there's a tendency for the Bogoliubov Fermi surfaces to be bigger along the 1-1 directions as opposed to the 1-0 directions. And so that may help in understanding other experimental results. Okay, so that's what I wanted to say about strontium-ruthenate. And now I'm going to turn to uranium-tellurium-2.
Daniel, just a very, very short question
Sure.
from me. So these Fermi surfaces are open? They're actually not closed?
Oh, yes. Yes, they are open. No, sorry. They're closed in this way. So this has the topology of like a torus. So they look like toruses. Does that answer your question?
Yeah, I'll just ask you more later.
But these are pictures of the Fermi surface?
These are pictures of the Fermi surfaces of the superconducting state, yes.
Uh-huh.
Yeah, and so, yeah, so they have so they look like a torus. Okay, okay, so I'll keep going.
Yeah.
Okay. All right, so now I'm going to turn to superconductivity in uranium-tellurium-2, and here I'm going to emphasize some new experimental results and provide some theoretical interpretation of those. All right, so this is a material that was discovered to be superconducting maybe a year and a half ago or so by Sheng Ran and co-workers. And right away in the original publication, you can see that this is an orthorhombic material, and you can see that there's very large upper critical fields for the fields applied along the B, A, and C axes. And you can see there's a lot of anisotropy between those fields, but the key point to realize is that all these upper critical fields exceed the kind of naively determined polyparamagnetic field that you just get from a simple BCS argument. And so that suggests right away this is a spin triplet superconductor. And in addition, uranium-tellurium-2 seems to be the sort of the end point of a family of uranium-based ferromagnetic superconductors. This family all seem to have ferromagnetism at a higher transition temperature, followed by superconductivity at a lower transition temperature. And uranium-tellurium-2 is nice in the sense that there is no sign of ferromagnetic order in this material. And so it's sort of the paramagnetic limit of these. All right, and so the usual understanding is that then the relationship to ferromagnetism also suggests this is a spin triplet superconductor. And so in the following, I'm simply going to assume that this is spin triplet superconductivity, and I'm going to say, what can we say about the order parameter and the quasi-particle excitations? And I already gave the answer to what I'm going to say about the excitations. Okay, so the first bit of information that helps us in determining this, I've already showed. And here again, this is this data from Aaron Kapitolnik's group by D.D. Wei. And so here is the polar Kerr effect that onsets at TC or around TC, and then is field trainable by a field along the C axis. And like I said, I'll come back to that. And so this tells us the superconductor breaks time reversal symmetry. You'll see more evidence of that in the next talk, in Vijay Madhavan's talk. And I'm not really going to talk very much about this. I'm just going to let her talk about this. One thing I mentioned earlier is that if we want to break time reversal symmetry in a superconductor, we need to have two components to the order parameter, and this requires some higher symmetry. And in fact, I mentioned already this is an orthorhombic material, and the interesting thing in this context is that all the superconducting representations are one-dimensional. I'll talk about these states in a little bit more detail later on, but in general, I've written down order parameters that can be arbitrary linear combinations of spin triplet vectors, and I'll talk about these functions in maybe 3 slides or so. But the key point here is that all the representations are one-dimensional, and so we can't really understand how it's possible to break time reversal symmetry with only one-dimensional components. So what is the answer to that? Well, the answer to that lies in the fact that it's, in the last year or so, it's been seen that there's actually multiple superconducting transitions. This was first observed by the Grenoble group, where they saw 2 superconducting phases that appear under pressure. That's denoted here. They were not sure what happens at ambient pressure, and so I'm showing this question mark that they have here. And this was revisited by Ian Hayes and co-workers at Maryland in Jean-Pierre's group, and they show clear 2 transitions for a variety of samples. And so there's clearly 2 specific heat anomalies suggesting there are 2 transitions. This has subsequently been also revisited by the Los Alamos group by Sean Thomas and co-workers. And they also look at the pressure dependence of these 2 transitions. And they have evidence that these 2 transitions cross here at this critical pressure at 0.2 GPa. And if I have time, I'll talk about some of the implications of that on some of the experimental results. Okay, so that's where the broken time reversal superconductivity comes from. We have 2 transitions. The second transition allows broken time reversal symmetry then. And I also mentioned I'm interested in the nodal excitations. And so here's some thermal conductivity on the nodal excitations. So this is a bit of a busy slide, but this is thermal conductivity along the A and B axes. It wasn't measured as carefully along the C axis. And the key thing to notice here is these red and blue dots. That corresponds to uranium-tellurium-2. And this orange line would be a typical fully gapped superconductor like niobium. And here you can see quite clearly that there's many, many more excitations here at, well, low fields being, or that developed by fields than there are in this niobium material. And okay, I didn't show the data here, but for people familiar with thermal conductivity, you remember if you have line nodes, you may get you expect to get a so-called universal thermal conductivity. There really isn't much of a sign for that universal term in this uranium tellurium-2. And so if you're going to suggest nodes, that really means that you have likely point nodes. So at the time when this data first came out, people were not aware of the possibility that this material breaks time reversal symmetry, and so the classification was done according to time reversal invariant states. And there it was believed then that the appropriate order parameter symmetries that could give you the point nodes were either B2U or B3U symmetry. Okay, so now what I will do is I will now talk about the implications of this, about the possible pairing states, and then also about the possible nodal structure. Okay, so I've already mentioned we have a D2H point group, and I've already shown this table before. One thing is worthwhile pointing out, we don't really know that much about the electronic structure of this material. There's some data to suggest that uranium F-electron fermions form a Z-point electric pocket, and that comes from ARPES measurements with Andrew Ray's data. And I think in Vidya's talk, you'll also see some information about the condo formation in this material. And so there is progress being made in this, but certainly if we're trying to describe a superconducting state, and we're describing functions F that depend on K on the Fermi surface, we really don't know what those functions are. And so the most prudent approach in that case is to include functions that have the appropriate symmetry properties, but we don't know their exact functional form. And so in this table, I've written all the possible combinations that are allowed by symmetry according to a particular representation. And I've defined 4 functions, fx, fy, and fz. And the key point is that fx behaves like kx, but could be something else like sine kx, or could be anything else, any function that has the same symmetry properties of kx. Fy is similarly like ky, and fz is similarly like kz. And finally, there's a 4th function, which I call fu, and that has the symmetry of kx times ky times kz. All right, so that describes this table, and in principle, any linear combination of these can form your order parameter. Okay, so the first question I want to come to then is, what is the implication of the fact that the polar Kerr effect is trained by a c-axis field? Well, that means that in your free energy, you have a term that's linear in the field along the c-axis, and the only way you can couple that to an order parameter in zero field is through this combination. And if this coupling exists, that puts symmetry constraints on the 2 components psi1 and psi2. Right? And so then you can ask what combinations of psi1 and psi2 can allow you to have this term in your free energy. And there's 2 possibilities. The first is an AU plus IB1U state, and the second is a B2U plus IB3U state. And so you're naturally led to these 2 possibilities. Okay, so now I want to turn to So now I want to turn to some more discussion about the nodal excitations. And since we have a spin triplet superconductor that breaks time reversal symmetry, we expect from that topological classification I showed you earlier that while points are possible. And I thought I'd give a little bit more description about these while points. I don't know, how am I doing for time?
Yeah, you have sorry, you have 4 more minutes.
Okay, so I think I
alerted you. So and just there's a short clarification question from Pavel Volkov. Is the training possible only for H parallel to the c-axis?
So the experiments are only for H parallel to the c-axis. I've urged to try for fields in plane, but due to just experimental geometry constraints, that hasn't been done. But I do think it's the best interpretation of the experiments is indeed it is the c-axis field that does the training. But that's a good question and something that should be revisited experimentally, certainly. Okay, so I thought I'd first give a little bit more of a microscopic picture of where while points come from in a superconductor, especially in a spin triplet superconductor. And so that's what this slide is doing here. So I have a spin triplet superconductor, which I'm going to characterize by D1 plus ID2. D1 and D2 are real, and I characterizes the broken time reversal symmetry. And years ago, Manfred Siegrist and collaborators worked out what the excitation spectrum is for this, this order parameter. And that's what's expressed here. And importantly, it has three terms. It has a usual epsilon k minus mu term, which is just the usual dispersion, the chemical potential. So this gives the Fermi surface in most cases. And then it has this plus magnitude of the gap squared, and it has this plus or minus qk. And this qk is an object we're not that familiar with. It's given by the cross product of D and its complex conjugate. So if D1 and D2 are real, and there is no phase factor, then D and D star are parallel and this cross product vanishes. And so this is a consequence of the broken time reversal symmetry. What's important is the magnitude of qk can't become bigger than the magnitude of D squared. And so I can characterize this plus minus by two gaps, delta plus minus squared, and both are going to be positive or zero. Right. And
Daniel, a short question from Eun-Ah. Is this material a quasi 2D or 3D?
That's okay. So the pocket that was seen is 3D, meaning it looks like it's a closed pocket. However, band structure calculations, LDA plus U, suggest there's also quasi 2D Fermi surfaces, and so it's a mixture. And so that's also part of the debate.
Thanks.
Okay, so let me come back to this. So I'm looking for nodes, and I have to set both this equal to 0, and I have to set the gaps equal to 0. So this tells me I sit on the Fermi surface, and now I have to look at the condition in particular that delta minus is 0. And so you can put in this D1 plus ID2 and work out for what kinds of D1 and D2 you get this delta minus equal to 0. And you find that for this to occur, you need the magnitude of D1 and D2 to be equal, and that has to happen somewhere on the Fermi surface. And you need the inner product of D1 and D2 to be 0, and that has to happen also at the same point at the Fermi surface. Ignoring the condition that we're on the Fermi surface, you can see that these two conditions define individually surfaces in a momentum space, and those surfaces will intersect in a line. And so these two conditions define some line that travels through momentum space, and that line can travel through a Fermi surface at points. And so that's where the while points come from, and this argument then tells you that they can generically exist in these spin triplet superconductors. However, generically exists doesn't mean they must exist. And surprisingly, with a fairly general symmetry analysis, you can see that they're what I'll call exceedingly likely in this particular B2U plus I B3U state. All right, and so what I'm going to do here is I'm going to work through the symmetry condition, in particular this condition D1.D2 equals 0, and tell you that we do get these while points for this state. And I'm going to borrow a little trick that we've learned from topological semimetals, so molybdenum ditelluride, and look at high symmetry planes where they find while nodes in these materials. And so I'm going to focus on the kx equals 0 plane. And the key simplification that happens when I consider kx equals 0 is these functions fx and fu must both be 0. And so if we look at what that means for the B2U and B3U pairing states, I can just cross out the components of this that look like fx and fu, and that's what I've done here. And you can see right away that dB2U and dB3U are orthogonal. This is along the x direction, this is along the y hat and z direction. And so I've automatically satisfied one of these two constraints. The second constraint is, can we ensure that the magnitude of D1 equals D2? And I found in the past when I try to explain this in a talk, it doesn't go over very well. So I'm just going to skip to the answer. I'm just going to say the answer is yes. And the answer happens in either the kx equals 0 or the ky equals 0 planes, but not in both planes at the same time. Okay. And the final picture we get then is a while node distribution that looks like this. You can calculate the while charge of these, and to be honest, we've done this numerically with a microscopic picture. But what we find typically is if you look at the KZ-KY plane, you have while charges of plus and minus distributed in this way. All right, and so the only thing I want to say about Vijay's talk is that if we have while points, we also have surface Fermi arcs. And perhaps these surface Fermi arcs are relevant for the chiral edge states that are seen there. So I'm going to guess I'm very close to the end of my time. Is that right?
Yeah, past a little bit past actually.
Okay, a little bit past. So I think I will not go over what I was going to say about some recent work on a microscopic theory. And if people are interested, the only thing I was going to point out that this gives some predictions for D vectors, which allows us to think about the response of these states to magnetic field. And in fact, if we think about that, we find that there's actually some very reasonable good experiment with the, some reasonable good agreement with experimental measurements of the response of this superconducting state to magnetic field. But I will just jump ahead to my conclusions now, and then I think open this talk to discussion.
Okay, thanks very much. Very, very interesting talk. So we're gonna open up for questions. And there was a question from Yushuan. Yushuan, if you want to raise your hand so I can find you easily, or if you want, I can just ask your question from the chat, if you're still here. Here, yeah. So I'm gonna allow you to talk. And you can
Okay.
unmute.
Yeah, Daniel, very nice talk. I just have a very brief question about the first part on strontium ruthenate with the Kz times Kx plus IKY symmetry, pairing symmetry. Naively,
Yes.
if I have just regular spin rotational invariant Fermi surface, what I would get for this kind of pairing symmetry is line node on the equator. So am I correct that the Bogoliubov Fermi surface is induced by the spin-orbit coupling of the system?
Yes, you are right. And the fact that we have multiple orbital degrees of freedom. So yeah, I've given maybe a quick picture of what happens generically. So indeed, you're right. So this is not really strontium ruthenate, but here this is the line node you're talking about, and this is a Kz, Kx plus IKY type order parameter, but in 3 dimensions that has point nodes up here and there. What happens is the superconducting state induces by itself a magnetic field, a Zeeman-like magnetic field that is momentum dependent. And what that does to the nodes that we originally had is that it, what we call, inflates them to form Fermi surfaces. And you'll find these Fermi surfaces are then quite close to the original line nodes and maybe point nodes that we would have expected otherwise.
Yeah, go ahead.
Yeah, would you be comfortable making a statement that in general these Bogoliubov Fermi surfaces involves spin-orbit coupling to some extent?
Actually, so almost would be comfortable with that, but I can think of one class of Hamiltonians where I can think of an exception. And so maybe in strontium ruthenate related cases, so this depends quite a bit on the role of parity symmetry in your theory and whether you have Vanier functions that are centered at sites of inversion symmetry or not. And if they are centered at sites of inversion symmetry, then I think, yes, spin orbit plays a key role. But if they're not, I think you can have other interactions that drive these Fermi surfaces.
I see. Thanks.
Right. So the next question is by Andreas Kreisel.
Yes. So my question is also about the Bogoliubov Fermi surfaces in strontium ruthenate, which
Yes.
I think have some thermodynamic kind of imprints in terms of large residual specific heat at 0 temperature. So now, would this be consistent with the experimental findings on strontium ruthenate?
Yeah, that's an excellent question. So the one thing I didn't emphasize in the talk, and maybe I should have emphasized, is the scale of my c-axis momentum here in reciprocal space. And so if you look, this is 10 to the 3 times the c-axis sort of reciprocal lattice vector. And this tells you that along the c-axis, this takes up something like 1% of the Brillouin zone. And so these features you're talking about, they're coming from something like 1% of the original density of states. And so I do think that they're going to be hard to see in this context. But I do think these Fermi surfaces are nonetheless important because it provides sort of nodes where nodes weren't before, in particular nodes at finite kz, which can lead to, I think, non-trivial implications in understanding other experiments like, say, thermal conductivity experiments.
Okay. The scale I didn't see.
Yes, I didn't highlight. I meant to, but I forgot.
Right, I missed that as well. Yeah. Right. So now there are a couple questions from our panelists. There was a question by Rafael.
Yeah. Hi, Dan. Very nice talk.
Thank you.
I'm curious what you think of the pressure experiments that you alluded to. One thing that confuses me in those experiments is that there seems to be a magnetically ordered state, right, that is induced with pressure. I know there's a debate whether it's ferro or antiferro, but regardless, no, sorry.
Sorry, I put up these
yes,
experiments.
These ones, right? What confuses me is that if both superconducting states are triplet, which has to be the case if you want to have the Kerr effect, of course, or they have to have the same parity.
They have to
why would one of them be essentially killed as you approach a magnetic phase and the other be enhanced? This would seem naively to be more consistent with a singlet and a triplet. I know this then contradicts the Kerr experiment, but I wanted to know if you have an idea about that.
Yeah, so I don't really have a great idea about that. I don't know if this is really a quantum critical point, so I don't know if this phase diagram exactly looks like what we might expect. But indeed, you're right, we do need to understand why it is that one TC and the other TC evolve differently under pressure. The idea of a mixed singlet and triplet is interesting. We heard that even raised by Thomas Scaffidi in the context of strontium ruthenate the other day, and then Andrew Mackenzie talked about this in the context of this serum rhodium arsenic material, but I can't really shed much insight. So the microscopic theory I've been working on explicitly includes ferromagnetic interactions and then uses band structures that come from DFT plus U calculations, and then also highlights some specific structural features of the crystal lattice in this material. And so I didn't tell you the conclusions there, but that's where I get my two states from, but it could be something else, of course.
Okay, thanks.
And there was a question from Steve.
Yeah, I just want to make sure I've got this straight. These Bogolubov Fermi surfaces are always closed. They have an inside and an outside.
Yes. Yes.
But there's no
arcs.
There's no Luttinger's theorem that controls the volume that they
exactly
enclose.
That's true. We have broken you one. Yeah, charge conjugation symmetry is broken. There's no Luttinger.
Okay, but you can't have edges. They really have to be closed.
Yes, they are closed.
Okay.
Yeah, the topological invariant is defined by the fact that there is an inside and an outside.
Okay, good.
What controls the volume then?
Yeah, so this, okay, so maybe I should have spent more time talking about these, but loosely speaking, Loosely speaking, I mentioned that there's a magnetic field that is created by the superconducting state, and this is generally an interband effect. So you typically want bands to sit close together. And what controls the volume of the Fermi surface is the magnitude of this magnetic field induced by the superconducting state.
Right.
While I still am up, there is an example of a Fermi surface without spin orbit coupling, which is if you had a D-wave superconductor and a Chandra loop ordered state.
Yes. Yeah, that's right. That's true. I mean, that breaks parity symmetry, and so for this,
it breaks all sorts of symmetries.
Right. So the next question is by Sr2RuO4.
Hi, Daniel. I'm just wondering, does the data of the curve rotation in uranium ditelluride show dependence on the disorders?
I don't think there's enough data to answer that. These results are relatively new, and that's a great question. So I'm sure once all labs are, I guess Stanford labs are up and running, and so presumably this can be checked. But I mean, I think there's a variety of samples that have been checked, but there's no controlled study of disorder for that.
Okay, thank you.
And there's a question by Yili.
Okay, thank you, Erez, and thanks Daniel for the very nice talk. I have two questions about uranium ditelluride. So one quick question: you mentioned d vector d1, d2. Do you mean you want to say you have complex d vectors?
So d1 and d2 are assumed to be real, and then the I is the phase factor between them that breaks the time reversal symmetry. So in my picture, this is, for example, what I call db3u and db2u. Those would be all real.
Are these d vectors?
These are d vectors, yes. D vectors like these ones here, where this would be real combinations of these three components that I show here.
So is your pairing non-unitary?
Yes. In fact, this Q here is the non-unitary part. But if you have spin orbit coupling in a material, then for any broken time reversal spin triplet state, it will be non-unitary, right? I mean, it's unavoidable.
Right. So did you check something like pair of Berry phase? You can define Berry phase.
Yes. So I haven't explicitly checked it, but yeah, I'm familiar with your work. And I think there are indeed close similarities between the states here and the states you talk about. And the pair Berry phase is relevant. But yeah, I haven't carefully explored that, to be honest.
That's okay. Thank you so much. And also one thing about the Fermi arc you mentioned, and also the vowel point. So here the vowel point, you mean the vowel point for the BDG Hamiltonian?
Yes, the Weil point for the BDG Hamiltonian, exactly.
So you may have particle Fermi arcs, whole Fermi arcs crossing the Fermi surface projection to the surface boson.
Yes.
I see. Sounds interesting. Thank you so much.
Yeah, so let's just take one more question. We have to move on. So, Oscar.
Hi, Dan.
Hi.
I assume that the Hund's mechanism you're referring to is the same as what Andre Topologically and I did.
It is exactly the same, yes.
In this mechanism, are there any nearby ordered states like Bardassis-Schrieffer modes? For example, if you were to look at a D plus IG, is it nearby?
Yes. So we find that there are two generic ground states in our theory. There's an A1G state, which is nodal, and there's an EG state. And both of these two states are actually close in energy. And so we play with some normal state Hamiltonian terms. Here's a spin orbit. We change it by a couple MeV, and we can drive a transition between these. And so those modes are likely to be there, yes.
Okay, thanks.
Okay, so we have to move on. So thank you very much, Dan.